In this section, we'll look at tokenization for LLM jobs, what it is, why it matters, and how to talk about it in interviews. Tokenization is the step that turns raw text into the units a model can actually process. It affects context length, cost, latency, and even output quality. If you can explain those trade-offs clearly, you'll stand out as someone who understands how LLM systems really work. This topic is a real separator in interviews. At the surface level, people say tokenization just means splitting text into chunks. But in production, it affects everything. How you design prompts, estimate cost, manage context windows, and chunk data for retrieval. For LLM, AI engineer, and agent roles, this is the difference between knowing the terminology and actually building systems that work reliably at scale. What actually happens under the hood is simpler than it looks. Your raw text first goes through a tokenizer, which breaks it into pieces and maps each piece to a token ID. The model never reads the original string directly. It works only with that sequence of integers, predicts the next sequence of token IDs, and then those IDs are decoded back into readable text. Here's a simple way to build intuition for tokens in English. On average, one token is about 4 characters, or roughly 3/4 of a word. That means 100 tokens comes out to about 75 words. So if a model has a 2,048 token limit, you can think of that as roughly 1,500 words of English text. These are rules of thumb. Not exact counts, but they're very useful in practice. Here's an important limitation. Non-English text often uses more tokens than English, because most tokenizers are optimized on English-heavy data. Languages like Chinese, Japanese, Arabic, and Tamil can take 2 to 5 times more tokens to express the same meaning. That increases cost, uses up context window space faster, and in heavily fragmented text, it can even reduce model quality and consistency. At the core of tokenization are 3 common subword algorithms. BPE starts with individual characters and repeatedly merges the most frequent pairs. That's what GPT models use. WordPiece takes a greedy approach, building the longest known subword first, as in BERT. Unigram works differently, choosing the most probable segmentation from several possibilities. The key takeaway is that the same text can produce different token counts depending on the tokenizer, which really matters in multi-model systems. SentencePiece is built for real-world multilingual text because it works directly on raw text. It doesn't rely on spaces between words, which makes it especially useful for languages like Chinese and Japanese. It's also reproducible. The model file contains everything needed to tokenize text the same way across different systems, and its vocabulary size is fixed in advance, letting you balance broader coverage against shorter token sequences. Tokenization is one of those foundational layers that affects almost everything downstream. It shapes what the model can understand, how much context you can fit, and how much each interaction costs. It also impacts the user experience because decisions like chunking, retrieval, and memory all depend on how text is broken into tokens. So if you want reliable, efficient systems, tokenization has to be treated as a core engineering concern. This slide is about the context window budget. Everything you send to the model has to fit into the same fixed space. The system prompt, conversation history, retrieved passages, and the output you want back. They all compete for tokens. Poor tokenization can waste that budget quickly, and the limits matter. Claude can handle up to 1 million tokens, while GPT-4o supports 128,000. So budgeting tokens is really an engineering discipline. When using LLM APIs, tokens are effectively money. You're billed for both sides of the conversation, the input you send and the output the model returns. That means inefficient prompting adds cost fast. Long system instructions, too much conversation history, or oversized retrieved context can quietly drive up your bill. OpenAI's own guidance is simple. Keep prompts shorter, chunk large documents, and summarize inputs when you're getting close to token limits. In a RAG pipeline, tokenization shapes almost every step. Ingest, chunk, embed, and retrieve. Chunk size is really a token budget decision. If chunks are too large, fewer of them fit into the model's context window. If they're too small, retrieval may miss the full meaning spread across nearby text. That's why token-aware chunking is such an important engineering skill for building accurate, efficient RAG systems. In an agent loop, token usage grows every turn. It's not just the latest user message, but also prior conversation, tool call traces, tool outputs, retrieved passages, and the system prompt overhead. All of that accumulates in context, often faster than teams expect. Without a clear truncation or compression policy, the loop can silently hit the context window, causing failures, higher costs, or degraded performance. Here are a few tokenizer tools every candidate should know. The OpenAI Tokenizer is great for quickly seeing how a prompt gets split into tokens and how many tokens it uses. TickToken is OpenAI's Python library for counting tokens in code and estimating cost. Hugging Face Tokenizers helps you inspect BPE, WordPiece, and Unigram pipelines. And SentencePiece is especially useful for multilingual or custom tokenizer workflows. Portfolio Project 1 is a context budget planner. It takes the system prompt, the user prompt, any retrieved passages, and the expected output length as inputs. Then it uses a tokenizer, like TickToken or a Hugging Face tokenizer, to count tokens for each part and estimate the total context cost. If that total goes over the target model's limit, it flags the risk and shows which component is taking up the most space. Here are two strong portfolio projects to showcase. First, a multilingual token audit. Take the same content in English and several other languages. Then, compare token counts and visualize the cost differences using the provider's tokenizer. Second, a retrieval chunking experiment. Test chunk sizes like 256, 512, and $24 tokens to see how they affect retrieval coverage and answer budget. Together, these projects demonstrate the kind of practical operational judgment hiring teams look for. Here are a few interview questions worth nailing. A token is just a chunk of text mapped to an integer ID, and that chunk might be a character, a subword, or a full word. Subword tokenization is usually preferred because it handles rare words, typos, and new strings more gracefully. Also know how BPE, WordPiece, and Unigram differ, and how to debug prompts that exceed model limits by counting parts and trimming strategically. Here's a quick side-by-side view of the main tokenization approaches. BPE builds tokens by merging the most frequent character pairs, which helps models like GPT handle new words by composing them from parts. WordPiece uses a greedy longest match strategy and is common in BERT-style models. Unigram chooses the most probable segmentation, giving more flexibility. And SentencePiece packages either BPE or Unigram into a language-independent reproducible system used in models like Llama, Gemma, and T5. Vocabulary size is a design trade-off you choose before training, not something you tune at runtime. A larger vocabulary usually means shorter token sequences, which can speed up inference. A smaller vocabulary gives you longer sequences, but it reduces the model's memory footprint. In multilingual models, this trade-off becomes even more important because a larger shared vocabulary is often needed to prevent words from being split into too many fragments. Here's a practical career path for working with tokens. First, understand the basics by learning BPE, WordPiece, and SentencePiece, and use the OpenAI Tokenizer tool to build intuition. Next, inspect token usage in code with TickToken and Hugging Face tokenizers. Then, build portfolio projects, like a budget planner or chunking experiment. Finally, apply that skill to real systems, making smarter decisions in RAG, agents, prompt design, and cost control. Here are the key takeaways. Tokens are the model's true interface because under the hood, it only processes token IDs. They're also the budget. Token counts drive cost, context limits, latency, and often output quality. Just as important, tokens are an engineering lever. If you understand them well, you can build systems that are cheaper and more reliable. And finally, a small portfolio of concrete projects is the best way to show that judgment to hiring teams.